Chapter 9 is devoted to roots and radicals. And I find that kind of interesting because if we were in a biology class and we were talking about roots, we'd probably be talking about plant life. And if we were in a sociology class and we were talking about radicals, we'd probably be talking about all those folks from the 1960s. But here in math class, what we're talking about is basically square roots and cube roots. And the word radical comes from the sign that's used for that. And you see there on the screen, we've got the square root sign and the cube root sign. That's called a radical. The first thing we need to know, though, is what are the perfect squares? If we take a square root of the perfect square, we'll get a whole number. The square root of anything else, for example, the square root of 3, goes on and on forever, so it's called an irrational number. But the square root of a perfect square, being a whole number, is considered to be a rational number. Now, there's a list of these on page 634, but I kind of want to go over these because these are the ones that I think are most important for you to memorize. If you have this list memorized, then it's easier for you to do it. So, if I take 1 times 1, I get 1. That one's pretty easy. I take 2 times 2 and I get 4. 3 times 3 and I get 9. 4 times 4 and I get 16. 5 times 5 and I get 25. 6 times 6 and I get 36. 7 times 7 I get 49. 8 times 8 and I get 64. 9 times 9 I get 81. 10 times 10 I get 100. 11 times 11 I get 121. 12 times 12 I get 144. 13 times 13 gives me 169. 14 times 14 gives me 196. And 15 times 15 gives me 225. I'm sorry, 225, not 222. Those are considered to be the perfect squares. So if we take the square root of these, for example, the square root of 4, and that's the symbol for square root, that's called the radical, then I get 2. Square root of 9, I get 3. Square root of 16, I get 4. And you can go on through that sequence. As you can see, it'll be 5, 6, 7, 8. You need to be able to recognize those immediately. And then you need to be able to know what's multiples of those perfect squares. For example, if you had 45, what divides evenly into 45? That's a perfect square. 9 does. So that's why you have to have a handle on all these perfect squares that I've listed there. And remember, when I take the square root of a perfect square, all I write down is the number 5. I don't write down 5 squared or anything else. It's just 5. So let's go ahead and do some sample problems in section 9.1. Those are on page 637. We'll only do a few of these. The first one is number 8. I'm thinking numbers 1, 2, 3, and 4 are very straightforward. In number 8, we have a minus sign in front. That minus sign then remains because it's outside the radical, and the square root of 81 turns out to be 9. In this second one here, number 14, what we're able to do there is break it into a fraction. The square root of 256 over the square root of 25. And the square root of 256 happens to be 16. And by the way, if you have a calculator and you punch 256 in there, hit the square root key, you'll get 16. That's 16 over 5. You could convert that if you wanted to into a mixed number, but that's the way the book will give you the answer, is 16 over 5. We've got a cube root here, number 18. The question is, what times itself 3 times gives you 64? And of course, you can look on page 634 and find it. But that happens to be 4. So the cube root of 64 is 4, but because we have that minus sign in front, it becomes minus 4. The interesting one, number 26, if you take negative 5 and you square it, what you end up with is the square root of 25. And the square root of 25 turns out to be 5. So in this particular case, even though they threw a negative sign underneath the radical, By the time you square that and get a positive 25, the square root of that will be 5. So that's something to think about. Now, in 9.1, all they're doing is some exercises involving perfect squares. So we're going to go ahead and move on to section 9.2. 9.2, what you're doing is simplifying a radical. So I'm going to scroll on down and we're going to take a look at how do we simplify radicals. And we're going to start on page 648. I've picked out a few sample problems. Now what we have is the square root of a number that is not a perfect square. But what we're able to do is we can break that into the perfect square times some other number. So what we do is we take the radical. What is a perfect square that divides evenly into 24? It happens to be 4. So I got 4 times 6. That turns out to be then the square root of 4 times the square root of 6. And that turns out to be then 2 times the square root of 6. All right? Now what I'm going to do from now on, starting with number 6, is instead of doing this one part right here, what I'll do is rewrite it as I did in the third part. So going back to problem number 2, when I rewrite it, what I'm really going to do is say, okay, what's the perfect square that goes into 24? It's 4. So it's the square root of 4 times the square root of 6. And that equals 2 times the square root of 6. How about 32? Well, 4 divides into 32, but is there a larger perfect square? And yes, there is. It happens to be 16. So if I break out the square root of 16 times the square root of 2, I get the square root of 32, but now the square root of 16 is 4, and the answer to that is 4 times the square root of 2. Now you'll see when we get to 9.3, what we're going to do is simplify some radicals so that we can combine those, but that's another lesson. Here we have the cube root of a negative 57. That happens to be really the cube root of what number is a perfect cube, and it turns out it is 27 times the cube root of 2. The cube root of negative 27 happens to be negative 3, because negative 3 times negative 3 gives me a positive 9. That times a negative 3 gives me a negative 27. So that's negative 3 times the cube root of 2. Now let's take a look at number 22. Here what we want to do is break out what is a perfect square that goes into 45, and I mentioned that earlier. That happens to be 9. And a squared is already a perfect square, so there's that part. And all we have left is a square root of 5. The square root of a squared is a. The square root of 9 is 3. So we have 3a times the square root of 5. In number 26, what we have here is the perfect square that divides evenly into 75. That's one that's pretty easy to pick up right away because 25 being a perfect square. So I know it's the square root of 25. And now a cubed is not a perfect square, but a squared is. What does that leave us? Well, it leaves us 3 and an a. So when I go ahead and solve that one, now what I get is 5a times the square root of 3a. Now we'll take a look at the cube root. 16 is not a perfect cube, but 2 times 2 times 2 gives me 8. So I want the cube root of 8, and x cubed is a perfect cube, because x times x times x gives me x cubed. What do I have left? The cube root of 2. Now when I break out that cube root of 8x cubed, I get 2x times the the cube root of 2. All right, so we've solved problems 2 through 30, the ones that we've picked out as samples. But now we want to take a look at some that are a little bit more challenging. We're going to take a look at the problems 48, 58, and 70. Hopefully I've got enough space that I can do that. In number 48, what I have here is a fraction, and I'm allowed to take that and break it into 2 parts. I can have the square root of 12y squared over the square root of 49. Now, in my numerator, 12 is not a perfect square, but 4 is. So if I break that into the square root of 4y squared times the square root of 3, I've got the numerator. And it so happens that 49 is a perfect square, and the square root of that happens to be 7. This then turns out to be the square root of 4y squared is 2y times the square root of 3 over 7. And if it so happened that they had used the square root of 64, and you got the square root of that being 8, you can actually reduce that fraction down a little bit. In this particular example, we can't reduce the fraction into any lower terms. Now let's drop down and look at number 58. What we're talking about with 58 and 70 is called rationalizing the denominator. Because I don't have a perfect square in the denominator, I want to create one. And the way I create one is I will take again and make this the square root of 12x cubed over the square root of 5. Now, to get a perfect square, if I multiply both the numerator and the denominator by that square root of 5, what I get now in the numerator happens to be the square root of 60x cubed over the square root of 25. Now I have a perfect square in my denominator, so the square root of that is going to be 5. But in my numerator, what do I have there? I have 60. Well, what divides evenly, that's a perfect square that is, what divides evenly into 60? Well, let's see. The only thing I can think of is 4, because 4 times 15 gives me 60. 9 doesn't do it, 16 doesn't do it, 25 doesn't do it. So all I have left is the square root of 4x squared, and then the square root of what's left, which is 15x. And now that's over 5. This then turns out to be 2x square root of 15x over 5. And that's our answer. For number 70, what we have is square root of 18 over the square root of a. Here, what I have to do to rationalize my denominator is multiply both the numerator and the denominator by the square root of a. What I end up with then is the square root of 18a over the square root of a squared. Now, a perfect square that divides into 18 happens to be 9. So what I have here is the square root of 9 times the square root of 2a all over the square root of a squared happens to be just a. And then this turns out to be 3 times the square root of 2a all over a. And I'm sorry if that got a little cramped on the right side there on the screen, but that's how you can solve the problems in sections 9.1 and 9.2.